Okay, welcome to Chapter 2 of our Zane State College Physics 2010 class. The first chapter was pretty introductory, some basic measurements and unit conversion stuff. Not really representative of what this class is all about. It's just kind of laying some basic groundwork. So this is where we first kind of jump into some actual physics ideas. We're going to start off by looking at kinematics, which is basically the way we describe the way things move. And we're going to start simply by looking at one dimension, so things that move in a straight line. So a lot of this class is problem solving. A lot of it is given a situation with some different variables. Can you then calculate various answers? That's what most of your homework problems will be like. And when you go about solving one of these physics homework problems, you essentially need to lay the ground rules. You need to set up some type of model to help you understand it. And so we need to understand this concept of frames of reference. So in this example here, it's from the textbook. If you're on a train, let's say the train is going 100 miles an hour. It's a really fast train. And you're walking from the back of the train to the front of the train. How fast are you going? Well, that's a difficult question to answer without establishing a frame of reference. Are we talking about how fast you're traveling with respect to the train itself? If so, you're probably only walking a couple miles per hour, maybe 2 miles per hour. If we're talking about your speed with respect to the ground or the rest of the world outside the train, then in fact you are moving at probably 102 miles per hour. So you need to make sure that when you set up a problem, that you clearly define the frame of reference, that you clearly define the parameters in which you are going about solving that problem. Another thing we need to clarify is the difference between distance and displacement. So in the example here, if I set this up, let me set up my pen with, just make it black. So we are starting, 1 second. There we go, got it set up right. So we're starting at this beginning point right here. So I'll go ahead and mention that it's a good idea to use the X and Y axes to set up your problems and to draw diagrams. So if we are talking about moving in just one direction, the y-axis doesn't really come into play so much. We're just basically talking about the x-axis, horizontal direction here. So you can almost think of it as a number line, and we're going to start at position 0. It makes sense to start at 0. So in one instance, in the dashed line here, we're traveling 70 meters to the east, and then we turn around and come back 30 meters to the west, and we end up at this point right here. Okay, in situation number 2, represented by the blue line, we start at the same point, and we just simply travel 40 miles to the east. Now, we, in both situations, have ended up in exactly the same place. Okay, but given the two different lines, the two different situations, a different distance has been traveled. So in the first case, we traveled 70 meters and then 30 additional meters. So the distance for the dashed line is 100 meters. For the blue line, the distance traveled is just simply 40 meters. So although there is a difference in distance traveled, each of these lines have the same displacement because they both ended up in the same spot. So displacement is how far from the starting point you end up regardless of how you get there. Okay? And so each of these lines have a displacement of 40 meters, but one has a distance of 100 and the other has a distance of 40. So we need to keep that distinction in mind. So some annotation, the way we write some of these things down. We're going to write delta x to represent a change in x position. Delta, this triangle, is the capital Greek letter delta, and is basically used to represent a change in something. The lowercase delta looks kind of like a lowercase d in our alphabet, but with a little bit of a squiggly top there. So whether we're talking lowercase or uppercase, delta generally in a scientific setting means change. So delta x is x2 minus x1, where we ended up, minus where we began. So we begin at x1, we end at x2. If we take x2 minus x1, that gives our delta x, our change or displacement in position. So in this case, we're going from x1 to x2. We're going from 10 to 30. So the displacement would be 30 minus 10 is 20. So here we have a positive 20 displacement going from left to right. So again, we set up these diagrams to represent what's going on. The x-axis starts at the origin of 0, and as we go to the right, it is positive. So generally speaking, we will consider motion to the right to be positive versus the position, the diagram over here, showing a final position, an ending position of 10 and a beginning of 30. So over here, if we take our x2 minus x1, we're saying we ended at 10 minus 30. We started at 30. 10 minus 30 is negative 20. So in this case, we have a displacement of negative 20. We're going to the left. And that's because we are setting up the situation using the convention that positive x displacement is to the right, negative x displacement is to the left. And so although the distance traveled in both of these situations is the same, the displacement is different. We have a positive displacement here to the right and a negative displacement to the left. So if we were to take the distance traveled and divide it by the amount of time it takes, that gives us speed. So you're probably used to the speedometer on a car in miles per hour, mph, or we could write that miles over hour, so a mile per hour. Distance divided by time gives us speed. Okay, in the metric system, we wouldn't use miles, we would use meters, and we would want to use seconds instead of hours. So we might say meters per second to describe speed. Okay, but speed is just talking about distance traveled, how far we went. If we include the direction that we're going, are we going from left to right, up and down, or some combination of the two, and include that, that gives us our displacement. Our displacement describes the direction we're going, and divide that by the time elapsed. That gives us something called velocity. So velocity is similar to speed, but it's different in that velocity includes direction. It is a vector quantity that is found by taking the displacement minus the elapsed time. Or, in other words, we could say that is the final position minus the initial position, because that is, after all, how we find displacement. So x2 minus x1 divided by t, or we might say delta t, okay, or we might even describe this, x2 minus x1, as delta x. So delta x over delta t just means change in position over change in time, gives us velocity. If I put a bar over that, that means average velocity. I'm going to skip over this slide. This is an embedded video. You can watch this on your own. It's basically just the scene from Despicable Me where Vector introduces himself. And I like to remind students of that scene throughout the semester because a vector is a mathematical quantity that has both direction and magnitude. And watching that scene is a good way to help you remember that. Let's look at this example problem here where the position of a runner is plotted as moving along the x-axis of a coordinate system. And we can see down here that the finish position x2 is 30. So x2 is 30. The starting position x1 is 50. And these are in meters, 30 meters and 50 meters. And during a 3.00 second time interval. So time is 3.00 seconds. The runner's position changes. And it looks like up here in the statement of the problem, it's actually given us 3 significant figures. So I should write that down. 50.0 and 30. Oh, it's 30.5. See, I couldn't tell that just by looking at the graph. I needed to read the problem statement. What is the runner's average velocity? So when you're given a problem in paragraph form like this, I like to write out the variables here in a list where it's easier to see what they are. And let's move on to the next slide here. So I've got that typed out here. x2 is 30.5, x1 is 50, time is 3.00. What is the average velocity? Well, the average velocity, delta v, is equal to the change in position over the change in time, which is equal to x2 minus x1 over the change in time, which is 3.00. And our final position was 30.5 minus 50.0. I'm going to divide that by 3.00. And that should give us, well, let's just do the numerator first, negative 19.5 meters divided by 3.00 seconds. If I advance my slide here to bring up, I have this all typed out as well. So what does it mean that this is negative? What is that telling us? Well, that just means that the direction along our x-axis is to the left. We are going in a negative direction. And a vector has both magnitude and direction, so that's the direction to the left. And if we divide that negative 19.5 by 3.00, we should get there, negative 6.50 meters per second. So we're just dividing our change in position by the change in time. The direction is indicated by the negative sign. So we're going to the left at a velocity, an average velocity of 6.5 meters per second. All right, I'm going to stop right there. I know I still have a little over a minute to go, but I don't want to get cut off in the middle of the next example problem. So this is a good stopping point. We'll finish here.